So in this video, we are going to talk about advanced Mapreduce topics. So far, whatever we've done would make us, let's say, someone who's aware of what is Mapreduce and how to design Mapreduce programs. And in this video, we are going to talk about how do you go about going to the next level of competence in Mapreduce. So let's get going. So the topics that we are going to discuss in this particular video are we'll talk about tool runner, we'll talk about unit testing Mapreduce programs, setup and tear down methods, Hdfs Api, distributed cache, running your job in local job runner mode, we'll talk about counters, we'll talk about Mapreduce streaming. These are the topics that we are going to discuss in this video. So let's get started. The first topic that we are going to discuss is tool runner. To understand tool runner, let's understand a bit of Mapreduce. Now, Mapreduce is basically written in Java, and once you write your code, you can submit it to the cluster. In our code, it's not a good idea that we submit our or we educate the program about our IP address and stuff. Imagine if you are writing your SQL query, in your SQL query, you don't hard code the IP address of your server. You want environment to take care of that. That is tnsnames.aura. Very similarly in Hadoop also, you are not going to educate where exactly is your cluster. It's going to be the configuration that will take care of it. So let's see how does this really work. So we have our Hadoop cluster. This is your laptop. In Eclipse, you write your code and you bundle that as a jar file. On your laptop, what you have is Hadoop client installed, and that's why you have files which are so when you submit your code actually gets submitted to the client, and the client will read these files and it'll actually submit two things. One is your code.jar and then a config XMLs. So this conf XML will basically have all the configurations, that is IP address of your cluster and so on and so forth. So all the details are present in this configuration file. So let's take example. On your client, in Mapreduce.xml, you have said that number of reducers is equal to 6. So what really happens is when you submit your code will run with number of reducers as 6 and you can't change it. So basically all this is completely configuration. So it's in Mapreduce.xml that the number of reducers are 6 and this goes in conf.xml. Now tool runner is a facility that's part of your Java code. So in our Java code, we will initialize a tool runner class. How to do that? We'll be seeing that in the code walkthrough. So we will have tool runner class, and this tool runner class will help us customize the behavior of this conf.xml. So take example. Right now the number of reducers are 6, but in our tool runner we've set number of reducers to 8 in our Java code. So the conf.xml has number of reducers as 6, but in our code we've said number of reducers to be 8. So when the code is submitted on the cluster will open both the files and settings, and cluster would say that So in a nutshell, what really happens is tool runner is a class that lets you have the facility of customizing a certain behavior or a configuration from the command line. So in the configuration, the number of reducers are 6 and that is fixed. But from the command line, when we run the code, we are free to change it to any number. And because we have tool runner called in our code, this will get honored. This will get honored. That's the intention of tool runner. That's the intention of tool runner. So how do you basically call tool runner? In our code, our main class, we will call the tool runner.run method. So that's our main class. When we submit the code, along with the code we will say so once we've submitted the code, the tool runner receives it that, oh, this code requires number of reducers to be 8 instead of 6, and tool runner will customize that for us. So the way you do it, the entire syntax is Hadoop char, let's say word count or char word count This is our way of saying that the number of reducers for this particular program are going to be 8. This entire concept is demonstrated in the word count walkthrough program. So now you've theoretically seen it. When you run the labs, you're going to see exactly same example, that by default the number of reducers for a Mapreduce program is 1, and we are going to run it with 1. And then later from the command line we will say, let's run this program with number of reducers as 6 or 8, and we would find that without changing the code we would have 8 reducers or 6 reducers, and we will have 6 output files. So tool runner is a facility that is given to you to customize a certain behavior of your code or of your configuration from the command line. That's the power of tool runner. That's the power of tool runner. So this is tool runner. So the next topic that we are going to talk about, so a quick reiteration, tool runner is a facility that lets you customize a behavior configuration from the command line. That's the behavior of tool runner. So the next topic that we are going to talk about, and we will be demonstrating tool runner in the lab. So the next topic that we are going to talk about is unit testing. So as of now, okay, so we've so far understood how to go about writing our Mapreduce code. But next important question is, how do we unit test it? So let's understand the whole concept of unit testing. Now, what exactly is unit testing? Let's first define that. So the entire concept of unit testing is all about testing each and every individual component of your system. Let's say unit testing of a car would be testing individually each and every component of your car. Now, in Mapreduce or in Java world, unit testing would basically mean testing each and every component of your code. So let's take an example. Email validation. What makes an email a valid email address? What makes a valid email address? So let's set the ground rules. So let's say first rule would be should have at least one or @ symbol. Second, should have at least one dot after the @ symbol. And to add, so first the string should contain, or the email address should contain at least one @ symbol. So first we should check. Second, should have exactly one @, and third, should have at least one dot after @. All right. So as a developer, we write a code. So far we are saying if it contains @, and then we are testing if it contains exactly one. If it does, do nothing, else return false. If yes, return true, else return false. So this is our code where we say that, well, instead of nesting all the if conditions, we say if the email address provided by the user contains @, if it does, make sure it contains exactly one. If it contains exactly one, don't jump into the conclusion, then test if it has a dot after @. We could very well nest it here. And if not, if it's not containing @, return false. If it contains @ but does not have a dot after that, then also return false. Now this is the code that's written by the developer. Now a unit test for this possible unit tests would be giving an email that says and expecting false, expecting false, expecting true. So these are potential unit test cases where we will submit or we will pass this input to this code, and here we will expect that if we will get false. If our expected result is equal to the actual result, then we say it's a pass test case, otherwise it's a fail test case. So for example, if I try to enter your office building without a proper identification card and I am thrown out, is that a pass test case or a fail test case? It's a pass test case, because the expected behavior is anyone without a valid identification should not be allowed and should be thrown out, and I am thrown out, so that's a pass test case. So the entire concept of unit testing is testing each and every individual piece of your code. Now in Mapreduce or in Java, the framework used for unit testing is called as JUnit. It's the most popular Java unit testing framework available. So JUnit is the most popular Java unit testing framework available out there. Problem is JUnit cannot be used to test Mapreduce code. JUnit cannot be out of the box used to test Mapreduce code, because Mapreduce has lot of additional classes required like mapper, input splits, input formats. That is why for Mapreduce we have a framework called as MRUnit. MRUnit is nothing but JUnit plus support for Mapreduce. So Mapreduce unit is nothing but JUnit plus support for Mapreduce. So MRUnit framework is 100% built on top of JUnit, and it is nothing but JUnit plus support for Mapreduce. With MRUnit, we can just test the mapper, we can just test the reducer, or we can test the entire Mapreduce code. So with MRUnit, we are free to test just the mapper, just the reducer, or the entire Mapreduce code. During our labs, we have a separate entire video talking about how to write MR unit test cases, and how to test them. So this is the concept of unit testing in Mapreduce. So as a developer, once you write your code, you should be writing your unit test cases, and with unit test cases, you are free to test only your mapper, only your reducer, or the entire Mapreduce code. And during the labs, we have a separate video talking about how to perform unit testing in Mapreduce. So a quick reiteration. Tool runner lets you So we've seen tool runner that lets you customize a certain behavior from the command line, and MR unit, which is a framework that allows you to unit test your Mapreduce code. The third topic that we are going to talk about is setup and tear down. Now, so these are the most important characteristics of Mapreduce program. Mapreduce function is called for each and every record, or mapper function is called for each and every record. So if I have 80 records, my map function will be called 80 times. When it comes to my reducer, if I have 4 unique records, that is 4 groups, reducer will be called 4 times. What we really need right now is, what if we wish to So the use case is that, okay, if I have 80 records, map function will be called 80 times. But what if before the map starts, we would like to read some lookup data from a file? Or let's say after we are done with the map or reduce, we want to clean up something. Do we have any facility for initialize and cleanup kind of a facility? Yes, and the facility is called as setup and cleanup. Setup can be called so it's executed once before mapper or reducer function is called. And it's executed so these are nothing but initialize and cleanup kind of methods, which is a facility where in the setup kind of method you can initialize a connection, you can read some lookup data, and in the cleanup kind of method it is executed at the very end of or it's executed after the last time mapper or reducer function is called, so you can perform some kind of cleanup, let's say closing a socket to a file or a data source. So setup and teardown are methods for that. So setup is setup, and for teardown the method used is cleanup. So these are some of the facilities that could be used. So this is setup and teardown. A quick summary of advanced topics. So in the very beginning of this course, we've understood how to write our basic Mapreduce programs. So we first understood what is Mapreduce, how to write our word count program. We also saw how to go about designing our Mapreduce programs. And out here in this video, we are learning what are the advanced topics, or what will take us to the level 2 of Mapreduce. We first seen tool runner that gives us flexibility to customize a certain behavior from the command line. We've seen MR unit that gives us flexibility to unit test our mappers or reducers or the entire program. And you have setup and teardown methods. Setup and teardown methods are basically the methods that let you initialize something or clean up something. So if you want to read some lookup data, setup would be the method to go for. And if you want to clean up the data, then cleanup would be the method to go to. So the next advanced feature that we are going to look at is Hdfs Api. So let's understand Hdfs Api. So far what we've seen is in the basic course that we could access Hdfs from command line. We can access Hdfs using scoop. We can access Hdfs flume. Then there are other facilities like These are some of the options which could be used to access HDFS. Above all of this, there is one more facility, which is so it lets you access HDFS from the Java code. So for example, the Java function mkdir will be equivalent to Hdfs mkdir. The Java function list status would be equivalent to Hdfs ls. The Java function would be equivalent to Hdfs put. So everything that you've been doing from the command line could now be done from the Java API. That's the power of Hdfs API. So imagine you coding a new product for your organization or for the customer, where you want to display Hdfs file system directly from your user interface. Hdfs API would be your best friend. So everything that you've been doing it from the command line could be done directly from the Java API. That's the power of Hdfs API. Now this Hdfs file system API is part of Hadoop package, and the beauty is it's generic in nature. Hdfs file system API is a part of Hadoop package, Hadoop Java package. It's generic in nature in such a way that you can even define which file system you want to connect. So you are free to connect to a local file system using the same API. You are free to connect to Hdfs file system API, or you are free to connect to Amazon S3 also. So it's a generic file system API that will let you connect to any file system that you would like to connect to. So that is Hdfs API. Lets you perform Hdfs operations from your very Java code. So this is Hdfs API. The next topic that we are going to talk about is distributed cache. So let's understand distributed cache in detail. So let's say along with our data, every time we are supposed to pass some lookup data. So let's take a small example. On our Hadoop cluster, what we have is basically some so we have data for website access from different devices. So let's say we have 10 petabyte of data. So this is entire data for our organization's website access. People have been accessing our data, and let's say we have 10 petabytes of data, and our manager wants to do a reporting. So day one, manager, let's say, wants to only have report for and certain devices, let's say 80 devices. Today the report required is 80 devices. This is day one. Day two, manager requires a report, but this time separate set of devices. Some 160 devices. Day three, the manager would like to have report on 8 devices. Day four, so what we see is that every day the lookup data is changing. Every day the lookup data is changing. Now the real question is, how do you pass this lookup data to the cluster? How do you pass this lookup data to the cluster? So let's say this lookup data, every day that we get, we will call this as device lookup.txt. How do you pass this information to the cluster? One legitimate way is, before you submit a program, put this on Hdfs, and everywhere the code is running, everywhere the code is running, the code is directly accessing this lookup file from Hdfs. Oh, that's a very, very bad idea. A very, very bad idea. What you would rather want is maybe some magic where instead of putting it on a shared location, what if this lookup was available to each and every slave? And that facility is provided by distributed cache. So let's understand what exactly is distributed cache. if the lookup data is these are some of the benefits of distributed cache. It's a facility that passes the lookup data to the slave machines, and the biggest benefit is distributed cache cleans up, that is, deletes the that gives you facility to have a different lookup file on every execution. So day one, our code would look like and day 2 we can have lookup1.txt but with different data, lookup 3 with a different data. That is how you go about running your code. That is how you go about running your code. As soon as job is done, the lookup data would be deleted. And one of the most important feature is distributed cache puts lookup files in the current directory of your code, so that code just needs to know the file name and not the path. So the lookup.txt is placed in the current directory of execution. In that way, your code just needs to know the name of the lookup file and need not have any clue about the path of it, because it's assumed that it's going to be in the current directory. We will be looking at one complete example of distributed cache in the videos. So this is distributed cache. Lets you pass lookup data to your Mapreduce program. That is distributed cache. The next topic that we are going to talk about is local job runner mode. Now, Hadoop can run in 3 modes. Hadoop can run in 3 modes. One is distributed mode, where you have master and multiple slaves, and we've already seen that in the basics videos. The other mode is pseudo distributed. In pseudo distributed, master and slave runs on same machine. We've also seen that in the basics video where on a single VM we are running a master and we are running a slave. And blessings for the developer, or blessing for the developer, is the third mode, which is called as local job runner mode, which Hadoop runs on local file and not on HDFS. The biggest benefit is Hadoop runs on a single machine on local file system, not on HDFS. That means all the Hadoop processes are running in the same JVM. Now the biggest benefit is a developer can debug the code right from Eclipse, and we are going to see that in the lab. So what we are going to see is we are going to run our entire Mapreduce code right on the local file system, and we can even attach a debugger to the code. We'll be doing it right from Eclipse. That's the benefit of local job runner mode. That's the benefit of local job runner mode. So local That's the benefit of local job runner mode. So let's pause for a minute and quickly reiterate what we've seen so far. The first mode, or the first feature after learning what is Mapreduce and how to code it, the first thing we've learned is tool runner. Tool runner lets you customize a particular setting from the command line. So if the configuration says number of reducers is 1, from the command line we can very well customize it. Second is MR unit, that's Mapreduce unit. Mapreduce unit is the framework that allows you to unit test your Mapreduce code. So you can perfectly unit test your Mapreduce code. You can only test your mapper, only reducer, or the entire Mapreduce code. Setup and tear down. Setup and tear down is a facility that lets you initialize something or clean up something. So setup is called once before the mapper or reducer function is called for the first time. Cleanup is basically called once after the mapper or reducer function is done for the very last time. So it's pretty much like initialize and cleanup. The next topic that we discussed is Hdfs Api. Lets you perform Hdfs operations right from the Java code. The next thing we saw is distributed cache. Distributed cache lets you look up data from your Mapreduce code. Lets you pass lookup data to your Mapreduce code. So the biggest facility distributed cache gives you is you can have lookup and every time change it. It's perfectly okay. The next thing we saw is local job runner mode. Local job runner mode is basically a mode which lets you run Java code in the local mode. That means you can perfectly run your code from Eclipse and debug the code. You can perfectly run your code from Eclipse and debug the code. The next topic that we are going to talk about is streaming. Hadoop streaming is a facility that lets you write Java or Mapreduce code in non-Java languages. Hadoop streaming is a facility that lets you write Mapreduce code in languages other than Java. You can choose language, can be like Perl, Python or Ruby. It's a blessing for non-Java developers. There are three important points. First, and we'll look at each and every point in a separate capacity. First, and the fourth important point is so these are the four important points to consider. We'll look at each and every point separately. First point is you can write Mapreduce code in any language provided the language can read from operating systems standard input and standard output. So be it Perl, Python, Ruby. So the way input is read is your input is read in stdin, that's your standard input, and your language or your mapper code will read from stdin, and when it comes to writing the output, it will write output to std out. So the language has to be any language that you choose has to be capable of reading from stdin and writing to std out. That's very, very important. Mapper and reducer can be written in non-Java languages, but advanced components like input formats and writables need to be written in Java. So in a nutshell, the point is you cannot 100% replace Java. Let's quickly look at the fourth point, that is you have convenience of writing code in non-Java languages, but you will certainly have performance penalty. Java is like the first class citizen on Hadoop, and other languages will certainly have the penalty, or you could say it's a second class citizen out there. And third point to reiterate, the iterator is not available out of the box. Let's understand that in detail. So in Java world, before reducer, you may get something like So in Java world, what you get is these are two iterable objects that you get. That means the reduce function will get this in first iteration, and in second iteration it will get this. So the reduce function need not keep track of the fact that key is changing. But this is what we would get in non-Java world, and the reduce function would have to keep track of it, saying if key is same, continue aggregating. If not, aggregate the value and initialize counter to 0. So as a developer, that's your responsibility to keep track of the fact that key has changed. Key has changed in streaming world. Now on a very high level, let's just say that just a couple of percentage of people would be using streaming facilities because Java is having better performance, or it's like the first class citizen on Hadoop. That's why streaming is not very popularly used. Let's just say that unless you have a very solid reason that you don't have skill set in Java, just stay away from the streaming idea. Just stay away from the idea of streaming. So that's the concept of streaming. So Hadoop streaming lets you write Mapreduce code in languages that are other than Java. Languages that are other than Java. And the last topic that we are going to talk about is counters. Let's you do bookkeeping. So let's understand the concept of counters, and in the lab we will be demonstrating counters. So let's say our problem to be solved is we have temperature data and we wish to find We have temperature data and we wish to find the average temperature of San Francisco for the last 10 years. Now so our solution would be average temperature of SFO. But along with that, we get some bookkeeping information. Let's understand what is bookkeeping. Number of records read, number of bytes read, number of output records. Now this is information that's not part of my core business logic but gives me incredible amount of useful information. So these are called as bookkeeping variables called as counters. These bookkeeping variables are called as counters. They're called as counters. Mapreduce provides them out of the box. But it does not stop there. As a developer, I can also let's say invalid was 9999, valid was everything else. So in our code we can initialize whenever we get a record that was 9999, we'll initialize the counter and increment it as +1 to invalid, +1 to invalid, and by the end of our program we may get our own counters, or we will get our own counters also. So this is our own bookkeeping. So by default, Mapreduce provides us certain counters, but as a developer, we have facility to have custom bookkeeping. That's the concept of counters. That's the concept of counters. So counters let you do bookkeeping. So these are some of the advanced features of Mapreduce that take you to level 2. So at level 1, we understood what is Mapreduce. We understood how to write a Mapreduce program. We understood how to design a Mapreduce program. What is mapper, reducer, combiner, partitioner. Then it's time to go to advanced, and this video helped you do that. So the first advanced feature we saw is tool runner. Tool runner lets us customize a particular setting from a command line. So we can customize any behavior which is default from the command line. The second is MR unit, which is a unit testing framework for Mapreduce that lets us unit test our Mapreduce code. Third is setup and teardown. Setup is kind of initialize and teardown is cleanup method. Fourth was Hdfs Api, which lets us perform HDFS operations from the Java code. Then we saw distributed cache that lets us pass the lookup data to our Mapreduce code. The next topic we saw is local job runner mode, which lets us run our Mapreduce code right from Eclipse and then lets us also debug the code. The next we saw is Hadoop streaming, where we can write our Hadoop code or Mapreduce code in non-Java languages. And then we saw counters that lets us do bookkeeping, So these are some of the advanced topics that we saw in this particular video. In the next video, we are also going to see some more advanced topics that are how to create your own custom formats, input splits. We'll understand that, we'll understand compression. So this is all about, let's say, advanced features of Mapreduce, the first part. In the next video, we'll see some more advanced topics.